material, almost certainly. If we run out a little bit on the waveguide at the end, we'll figure something out, okay? So we'll cover all the material. So today I'm going to go through section 6 because it's very important. This is the most important lecture, I would say, okay? So you should definitely pay close attention to the stuff I'm going to ask you to do, including the examples. So cyclotron, synchron radiation today. We're going to do Bremsstrahlung and Cherenkov on Monday, and then we'll come back to the waveguide section. In the meantime, please read through that waveguide section and try the examples. Okay, you'll find that very useful to do. Okay, so now we're bang on time. I'm going to talk about the other sources of radiation. Now, the thing I'll point out as well, in general, you should be referring to the typed notes for guidance for what is going to be in the exam. And in particular, there are examples I have put in, both in the notes and in the examples questions, and you really, really ought to do those examples. Work through each of them. It'll pay you dividends, okay? Can't give you more information than that, can I? Now, cyclotron radiation. So we come back to our old friend, the Larmor formula, which we all know and love, and we notice that that is the power emitted by any accelerated charge, just like before, okay? And we recalled that in an antenna we had electrons going up and down, okay? But it could be any other charge in principle, just electrons are the things we happen to find in our copper conductor. And we notice there's a factor 2 that appeared here because this is the average power, okay? The reason the factor 2 is there is because the acceleration of the charges is changing as a function of time, okay? We had some kind of antenna, and the electrons were sometimes stationary at either end. That's one way to think about it, isn't it? Okay. Now we can think, is there another way to accelerate charges which is different to this? And indeed there is. And this is the concept of the cyclotron, which I shall fold over here so you can continue to see that bit. So here is a cyclotron, okay, in pictorial form. Okay. You have a magnetic field which is pointing transverse to some kind of chamber in here. And that chamber is where the protons are. So if you look closely, you'll see there's little arrows. The protons, in this case, are going counterclockwise inside that chamber. There are also little other things called Ds that provide a voltage to accelerate them. We're going to ignore that. The important thing is that no matter the radius of the protons in that chamber, remember the radius is proportional to the energy, which I'll show in a second, they will receive an acceleration and therefore they should be radiating. The crucial difference here is that the acceleration does not change with time. Wherever the proton is, as it goes around that circular orbit, it will experience a constant acceleration, and therefore it should be radiating constantly. So whenever we calculate, we should have no factor 2 appearing from averaging out, because the velocity and the acceleration is constant. Okay? So that's the concept of the cyclotron. Extremely technologically important. Here is a real one. This is Ernest Lawrence, one of those scientists that you should pay attention to. A great scientist and also a horrible person. It seems to be a thing that we learn more and more as the years go by. I hope I'm the former, not the latter. Maybe I'm the other way. I don't know. Anyway, that was the other person, the PhD student. So those who got into graduate work, he got the Nobel Prize, and this one didn't. But he did a lot of the inventing. That's a bit of a moral tale that you all also wish to may take away from you. But this is the chamber in here that we just saw, right? Okay. So this chamber here on the right is that chamber there. So that's the North Pole and that's the South Pole. And all this stuff here is basically this is a big coil of current that's driving the magnetic field in there that the protons are seeing. Okay, so that's how it works. Okay? This thing here is just a big return yoke that takes the magnetic field and stops it spraying around the rest of the room. Because of course if there's a North Pole there must be a South Pole at the other end of that magnet. So that just captures that field and turns it around. Okay? Modern cyclotrons look better than that, but anyway, that's an original one. Okay, so that's what a cyclotron is. So here's one I prepared earlier. Okay, so a cyclotron is a round electromagnet. The protons are going around the inside, and to first order we're ignoring the fact that there's an electric field. So we apply our old friend here, the Lorentz force. We obviously know that F equals QVB. We have circular motion, and as always, no work is done by the field on the protons. The work that's being done is by the protons on the radiation field. That's the energy equation. Okay? So whatever energy the protons lose as they go round and round in a circle is being given into the radiated field. It's got nothing to do with the magnetic field. Okay? I'll leave that at the top. Maybe I can't. No. Let's derive. It's in the notes. You can see it in the notes. Okay? So, interesting question is, what is the acceleration? Well, the acceleration, okay, for the proton of a single charge E is simply EVB over m. Okay? And if I equate forces equivalently, I can say that any given radius r, I can equate the centripetal force to the Lorentz force. Okay? And this allowed Ernest Lawrence to get a Nobel Prize in a few lines of working plus building it. You rearrange this equation and you find out that the radius is simply equal to mv over ev. That's not the Nobel Prize. The Nobel Prize was realizing something else. If I calculate, remember that 2 pi r is the circumference, I can work out what the frequency of revolution of the protons are. It's simply EB over m. That's the angular frequency. The most important thing to see about the angular frequency is there's no velocity in that equation. It's independent of the velocity. So if we look back at our picture of the cyclotron, the radius of the proton orbit doesn't matter. It is the same frequency of orbit. So if I have a variety of protons of different kinetic energies, different velocities, they will all go round together. And because they go round together, remember that the frequency of emission is equal to the frequency of their oscillation. So viewed from the side, right, even though the protons are doing this, viewed from the side, from any particular direction, they're just moving sinusoidally backwards and forwards, aren't they? So they look like a Hertzian dipole, just like if it was an antenna. So they still radiate, and they still radiate at the same frequency. They radiate at the cyclotron frequency. Okay? Now that's the angular frequency. We obviously want to write down Fc equals 1 over 2 pi ev over m. We divide by 2 pi. That is the cyclotron frequency. Now if you put in a field of 1 Tesla, right, this is 1 Tesla, you know the mass of a proton, well you know what that is. Okay? That frequency is something like 15 megahertz. Okay? So if you stick protons into a cyclotron, and the field from that magnet is a Tesla, they go around 15 million times a second. And that is the same as the frequency of emission. It's 15 megahertz. Okay? Quite low, quite a long wavelength. We haven't said anything at all about the power yet. We also haven't said anything at all about what else is happening in the cyclotron. And I'll just note, just by putting this up here, okay, the purpose of those Ds, because actually, as we're going to find out, cyclotron radiation is very weak. We're going to see that synchrotron radiation, which is the other thing that's way more interesting, we'll get to that in a minute. Okay? Synchrotron radiation is way more interesting and much more powerful. Cyclotron radiation doesn't really matter in a cyclotron. It is there. What's really going on that's dominant is actually there's an electric field across these two Ds that's accelerating those protons, and that's what's making them go to a larger and larger radius. Okay? But on their way, their revolution frequency doesn't change. Okay? Now, let's work out how much power is being emitted. So we put in our Larmor formula. P equals E squared, omega C squared, V squared over 6 pi, epsilon naught C cubed. So again, we see there's no factor 2 because the acceleration is a constant. We see now that because we work out what the acceleration here was omega C V, right? Put it up here, okay, is equal to omega CV, if I write it down carefully. So you see that the power does depend on the velocity. So it's the protons on the outside of the cyclotron, the ones with the higher energy, and the ones with the larger radius, they're the ones that are being accelerated more, and they're the ones that are emitting more radiation. It goes as velocity squared, it actually goes to the kinetic energy, doesn't it? Okay. But there's no factor 2 here, because the acceleration is a constant for any given proton velocity. Now, where does that radiation go? It's just like any other Hertzian dipole. Okay? So here's my cyclotron. Let's put it back on the screen. Okay. Viewed from the side, the protons are going horizontally, aren't they, when viewed from any particular direction? Right? So that means that there is radiation going this way, up and down. Okay. Is that right? I think that's right, isn't it? And viewed from any direction, it should be a constant, shouldn't it? Because the acceleration, the motion of the protons looks the same, whichever way around I look. Okay. So that's what we see. We don't see it, instantaneously, we look along one tangent, we don't see any radiation because there's no acceleration in that direction, and we're looking along the line of sight of the proton. Okay. Is that all right? Okay. How do you think about that? Okay, let's work out what the total power is. The total power, if we plug in those numbers and we put in 1 Tesla, it's 10 to the minus 22 watts per proton. In other words, nothing. No radiation is emitted. It's tiny. Okay, so a good calculation, one of the example sheets is, if the proton is sat there with no acceleration, it's just orbiting in a magnetic field, how long will it last? Okay. Work out that number, it's in the example sheet, and the answers will come around later. An interesting related fact is this is an identical calculation. If you look in the Feynman lectures in physics, this is the same calculation for how long an orbiting electron will last in an atom. You probably recall that in the original model of the atom, when I have a classically moving electron, it was this statement about the radiation being emitted which led to the conclusion that it had to be quantized. Okay? So there should be an equivalent lifetime for an electron and atom. The difference, of course, in an atom, firstly, it's an electron. That shouldn't change anything here, but the velocity is obviously different. But the acceleration is much greater because the object is much smaller. The forces are bigger when you're closer to the atom. Now, in reality, particle accelerators have many protons going in them. We count those either in number of protons or in the charge that they have. And again, the example sheet will tell you how to do this, so you need to work through that. If you have a picocoulomb of charge, then the amount of power emitted is something like 10 to the minus 16 watts. Okay. So a picocoulomb is a typical number of protons. It could be 1,000 times that, it might be a nanocoulomb. But for 1 picocoulomb, it's 10 to the minus 16 watts. So for a nanocoulomb, it's 10 to the minus 30. It just scales linearly, doesn't it? It's still nothing. It's basically zero, but it is there. Okay. Now, that's cyclotron radiation for a small amount of charge. There are other situations where it can be big. Imagine I have a large number of protons, and it could also be electrons, because remember, it doesn't matter what the actual nature of the charge is. All that really matters is the acceleration on that charge. So let's imagine a plasma, but now it's placed in a magnetic field. Okay, there's two obvious contenders. One is one of those fluorescent tubes in the ceiling there, and what I do is I put a bar magnet up against it. So whatever the protons and electrons are doing inside there, or even the ions, they will be accelerated and they should emit radiation, shouldn't they? The other one, which is a bigger scale, is a tokamak, where I have maybe a bigger magnetic field and a lot more plasma. In both cases, we can simply calculate the total emitted power as being equal to the same formula we had before. That was easy. I simply multiply it by the number of charges. Now, why have I written down only the number of electrons? Well, that's because if I have a certain magnetic field, the acceleration of the electrons is greater. So if I have a plasma composed of positive ions and electrons, it's only the electrons that are emitting. Seems straightforward, doesn't it? Now I can recast that. Now have a look in Bikhafi for a full derivation of this. I've tried to put it also into the notes. If you carefully plug these numbers, and I can't stress enough how easy it is to make a mistake, that's why I'm asking you to do these examples. Get used to doing the numbers in the calculator, okay? Very, very easy to get wrong. Do them a couple of times to show yourself that you can calculate it reliably. If I rewrite that velocity in terms of the kinetic energy of the electrons, and I give this kinetic energy here in EV, then this is the number of watts emitted per cubic meter. Okay, there's an overall scaling factor, and NE here becomes the electron density per cubic meter. It's a way of scaling that. Okay. So again, what do we see? This is crucial. Remember we said that the power emitted, or the radiation emitted, has a very, very well-defined frequency. This is the basic rule of cyclotron radiation, antenna emission, or anything, I'm going to say now, which is moving classically. Okay? So when we look at the frequency spectrum, a single frequency is emitted at omega c. Okay? That's the emission frequency, or the cyclotron frequency, if it's in a cyclotron. Okay? In fact, we still use the term cyclotron frequency, even in the case of a plasma. Okay? The cyclotron frequency is EB over m, where m is the mass of the species that's moving in the field. Okay? And it can be QB over m if the charge is not a single charge. Okay? And so we have a single frequency emission, and it looks like a Hertzian dipole. Now, the fact that it's not quite narrow is to do with the time variation of the emission. And another thing is, if we have non-uniformity of the field, we expect to see harmonics. Okay, so the strength of the harmonics in the emission, this is not an examinable statement, by the way. Okay, the strength of the harmonics is to do with the non-uniformity of the field, okay? Because we're getting a varying acceleration. Because we have a periodic motion, that variation must have some periodicity itself, and we have well-defined harmonics. Okay, that's cyclotron motion. Now we can also go through McAfee, and again, there's a figure in McAfee figure 14, if you use the same edition that I had, which is one of the older ones. Okay, and we remark to ourselves, what is the typical electron energy in a fluorescent lamp? It's about an eV, let's say. Okay. And we put a magnet up against it, so let's calculate that the magnetic field is maybe of order 0.1 Tesla. And in a fluorescent tube, it turns out the typical electron density of the plasma, okay, if you compare that to solid densities, it's quite low, 10 to the minus 17, 10 to the 17 per cubic meter. And again, we see, so what we say is, let's say one of those fluorescent lamps, I put a bar magnet up against it, and the power emitted is very, very small. Okay, it's like 60 microwatts per meter cubed. Okay? And because, of course, that tube there is a lot less than a meter cubed, it's less than a microwatt of power emitted. Yeah? Nothing. But it's a different frequency. It's completely different from the fluorescent light frequencies, right? Which is near visible or UV, actually. However, it's quite detectable because it comes out at 2800 megahertz. 2.8 gigahertz. Not far off a microwave oven frequency, is it? So we'll see microwave ovens, the magnetron that powers a microwave oven, also the device that makes the power is like that. It's electrons moving in a magnetic field of about 0.1 Tesla. That's where the microwave energy comes from. Okay? It's the radiation of low energy electrons. So you can see here the cyclotron frequency for electrons is something like omega c, something like 28 gigahertz per Tesla. Okay? Now, there's a basic issue that we're going to have to remark upon, which is, let's look back at our cyclotron. So here we have some protons going round, and they're going round in a circle because there's a magnetic field acting upon them, and they radiate. And you think, okay, where does the magnetic field come from? Well, the magnetic field is being generated by these coils up here and down there. So there are electrons going in the wires that are accelerating. They're accelerating because they're seeing some kind of force from the cables themselves, which is making them turn around in a circle. So those electrons are also accelerating, right? Don't really know how fast they're moving, but they should be radiating, shouldn't they? Okay. So that you should reflect on that as being a bit of a conundrum, because we remark, and we shall see this again a little bit when we talk about coherent radiation, if I have a steady loop of current, it does not radiate. But an individual electron does radiate. How can we describe that difference? Well, a steady loop of current has two potentials, a scalar potential and a vector potential, and clearly those in a steady current situation, those do not change as a function of time. Okay, so my steady current creates a steady vector potential. This is one argument for saying that there's no radiation. But that's a bit unsatisfying, because we realise if I had a very large number, let's say we turned the electron charge very, very small, and we had a finite current composed of very, very many small electron charges, each charge should be radiating, shouldn't it? And yet somehow this picture says it shouldn't. So how do we resolve that? Well, it is certainly true that each electron, when it is accelerated, radiates. Okay? But if I consider any two electrons, say, on opposite sides of that circuit, in the far field, those radiation fields cancel, at least when viewed from one direction. If I have a large number of those electrons, you can see, I hope appreciate, that the radiation field at any given instant, this one is accelerating this way, and that one is accelerating that way, and so on. They should all cancel out. So that's one argument for why a smooth distribution of current does not radiate. And the key thing here is sufficiently smooth. I'm saying that this is not an examinable thing, by the way, but hopefully you find this pretty interesting. So clearly, if I have a non-smooth distribution of charges, I should get a degree of radiation which is proportional to how non-smooth that distribution is. Yeah, that kind of makes sense, doesn't it? Okay. So the radiation field should have imposed upon it some kind of Fourier transform of what the electrons are looking at. And by the way, this was Thomson's original argument. He said originally that electrons did not spiral into a nucleus because they clearly were not discrete objects in an atom. They had to be smoothly distributed around the circumference, and therefore there was no time-varying potential. Okay, so the continuous distribution of charge around the atom is what gives me no radiation. That was the argument. We now know that is incomplete. Okay. All right. So that is cyclotron radiation. What is synchrotron radiation? It's exactly the same, but not quite. Okay. Synchrotron radiation. We have the same situation. We have a magnetic field pointing, in this case, into the plane of this paper, and we can imagine a variety of charges moving, and they will move in a circular path, and they will move with a revolution frequency, which is the cyclotron frequency. You can see this is 15 megahertz per Tesla for protons and about 28 gigahertz per Tesla for electrons. It's also known variously, I should point out here, it's known as the Larmor frequency because it's because of the Larmor radiation. It's known as the cyclotron frequency. And for things like magnetrons, fluorescent tubes, electrons in plasmas, things like that, it's also known as gyration. The motion is called gyration, which will have a certain equivalent radius. Okay, so the energy tells you the radius. So there is a gyration frequency. It's all the same formula. It's all the same process. But let's think about electrons. An electron with a large enough velocity, in fact any charge with large enough velocity, but electrons are the ones that have the low mass, so they're easiest to get to a large velocity. The important fact is that the mass increases. So there was something we missed, which is this is incorrect. This m is not constant. So as the electron increases in velocity, the cyclotron frequency drops by a factor of gamma. So I should really put m0 for the rest mass of whatever charge it is. I now have a factor of gamma. So it wasn't really true that the protons all go around at the same time. For protons, it's true enough. Okay, up to 20 MeV protons, it's true enough. And again, in the notes, there are some specific calculations to do. Let's calculate what that is. And this is something which is insufficiently done in the undergraduate teaching, so I'm going to point it out here. Let's imagine two kinetic energies, 10 MeV and 250 MeV. And I'm going to treat separately protons and electrons in each case. And we're going to calculate gamma. Okay? So, show yourself later that a 10 MeV proton has a gamma which is really, really, really close to 1. Why does that matter? That means that when I feed in that voltage into those Ds, I can leave my power supply at a constant frequency. I can have all the protons at different energies, and they're all happily getting that voltage kick as they spiral up in energy, and they can all go around together. In other words, I can make a cyclotron that works. Very important fact. Yeah. Now, an electron with 10 eV kinetic energy, well, gamma is obviously 20. So now, the cyclotron frequency falls by a factor of 20, so I need 20 times different frequency for the electrons on the inside compared to the electrons on the outside. And that means there is no such thing as an electron cyclotron. There is a thing called an electron cyclotron resonance, but that's for... There is a thing called a cyclotron frequency, but obviously it can only happen for extremely low energy electrons. We're talking 10 kV, 20 kV electron energies. And those are the kind of electron energies you can get from any hot cathode. So there's no point in having a cyclotron at that low energy. So that's why there's no such thing as an electron cyclotron. Now 250 MeV is completely different. For a proton, gamma is about 1.3. Now that's still significant, but if you go down the road to the Christie Hospital, they have a proton cyclotron, and it ejects protons at 250 MeV kinetic energy, so clearly it can be done, and you have to change the magnetic field, right? So rather than changing the frequency, according to gamma, you make B match gamma, so as the particles go out, you change B so you keep the same frequency. That's the other way to fix it, but it only works up to about gamma 1.3. So it still sort of works. For electrons, gamma's 500. Okay, that's massive, isn't it? So the first thing you should say there is the velocity is basically c. You don't care about the difference. Beta is equal to 1. You don't need to include that in your formula if it happens to pop in there for some reason. And the other thing is the kinetic energy is basically equal to the total energy. You can ignore the rest energy of the electron for all intents and purposes. Okay. All right. Now, let's look at what an electron is doing differently to a proton when it has a relativistic velocity. Or compare a non-relativistic electron. So here is a non-relativistic electron moving in some kind of circle, say that way. At any given instant, the acceleration is this way. So the radiation pattern is a Hertzian dipole, right? So if you superimpose all the different accelerations of the different azimuths, then you'll see actually there is radiation going up and down. There's radiation going kind of everywhere, isn't there? It just isn't going. When you look here, you don't see the radiation from the electron at that instant, but you do see it if you happen to be looking there or there. Okay. Now, if the electron is moving relativistically, a lot of things change. So this is non-relativistic and this is relativistic. The first thing we think about is what does the radiation look like from the point of view of an observer? Well, let's draw what it looks like and explain why. We will see that when viewed by an observer, we have an enormous narrowing of that radiation lobe. Yeah, this radiation lobe here is narrowed in the direction of the motion of the electron. And the first thing to realize is that width, the angular width, is 1 over gamma. So you can appreciate that must be coming from a Lorentz transformation. So the angular width of the radiation is of order 1 over gamma. And that's simply doing a Lorentz transformation of that radiation pattern here so the electron itself is emitting as a Hertzian dipole. When you Lorentz transform into the rest frame, we get this 1 over gamma in the radiation pattern. But there's something much more important, which is think about the instant when the electron is passing by such that that radiation beam is seen by the observer. What does the acceleration look like? Well, the first thing is imagine that the electron is moving in a circle. When it's here, the velocity is this way and the acceleration is that way. So the Lorentz transformation of the acceleration is just the same as it was before. Here, we have a difference in the apparent acceleration. Okay? The reason for that is that there is a dilation in time. Okay? So because the acceleration looks like it's occurring over a longer time, because the acceleration is seen by the electron is just the same as it was before, but the electron is seeing that apparent acceleration for a longer time because of the Lorentz transformation between the two frames, and that factor is gamma. Okay? So because the time is dilated by gamma, the apparent acceleration, okay, must be equal to gamma squared times the acceleration experienced in the electron's frame of reference. It still sees the same field. So the apparent acceleration is gamma squared times the acceleration in the electron's frame of reference, which means that the power is much, much bigger. So we have the same formula we had before. Okay? Everything else is the same. But I need to add on, okay, a gamma to the fourth, because the acceleration, okay, now just notice there is actually a typo in the handwritten notes. The type notes are fine. Okay? Because remember, the acceleration is still omega c squared v squared in the electron's frame of reference. But now when I transform to the rest frame, to the observer frame, there's a factor gamma squared for every factor a of the acceleration. And this is extremely important. The emitted power, apparently, goes up by a factor of gamma to the fourth. It's just simply enormous. Let's look back at our protons and electrons. Our 250 MeV proton, which as we saw is a pretty hefty energy for a proton. Gamma is about 1.3. Okay? So there's no significant increase in the power. But for our electron, of exactly the same kinetic energy, 250 MeV, and the reason I quote those is because those are common or garden energies you would encounter. You can make a cyclotron for protons of 250 MeV, you could make an electron LINAC or a small electron storage ring with 250 MeV electrons, and they're comparable numbers. Okay? Here, gamma, of course, is 500. So gamma to the fourth is of order 10 to the 11. Okay? It's massive. This is why we use electrons when we want to make radiation, because the gamma factor that we can get is way, way bigger. And this is the brightest source of radiation you can artificially make, because there isn't a brighter one, and it's simply to do with that gamma factor. So our basic system is we have a source of electrons, right, like a heated cathode. We distribute them somehow, get them up to a high enough energy, and we start circulating them in a so-called electron storage ring. And as long as the energy here is of the order of, say, well, this is order GeV, order 1 GeV, I get phenomenal amounts of power. Okay? Now, take a moment to stop. So the key idea here, again, go through the notes again. The key idea is that the apparent acceleration is changed because of that time dilation. Another way to think about it is the same acceleration, but the observer is effectively seeing it for more time, or the electron is seeing it for more time. That's our physical argument. You can get the same answer by looking directly at the Relativistic potentials. Hello? Sure. Yes. Yes, exactly. Yes. Exactly. The key statement is that all the formulae stay the same apart from the gamma to the fourth that goes on top. Okay? And the way to understand it is that you can think of it maybe as the electron is emitting at the same rate as it always was, but when viewed from our point of view, we're seeing that time dilation effect. And because the power goes as A, which goes as 1 over T squared, we're seeing gamma to the fourth more power. Okay? There's a variety of arguments here. None of them are very, very convincing. You can get obviously the same result from the Relativistic potentials. You can go to any textbook to look through those, but they don't tell you the physical reasoning why. This is a pretty good physical reason. Okay? This is one of the harder things to accept, I think. I mean, the mathematics is straightforward enough, isn't it? But it's Yeah? You have to convince yourself. But it's certainly true. It's experimentally, of course, true. Right? Now, there's something else that's going on. Because, imagine now the electron, which I'll just put my previously drawn picture, if I can find the damn thing. Here it is. Nice picture instead. Now imagine my electron as viewed by that observer. So we've already said that the Hertzian dipole pattern, that isotropic pattern, has been narrowed into a beam of radiation which has an effective width 1 over gamma, okay, of order 1 over gamma. So two things happen. Firstly, when the observer is watching the electron go by, this is separate from the consideration of the power. This is what the radiation looks like. If it was non-relativistic, I would see a smooth emission of radiation at a single frequency. But that's no longer the case because an observer looking along one particular tangent, this is what you will see practically, okay? You will see either no radiation or you will see radiation, and that has an apparent pulse width of 1 over gamma compared to the revolution frequency. Yeah? So I see pulses of radiation. But as well as that, the radiation, as the electron is moving slightly slower than the speed of light, okay, again the difference is a factor of gamma, the radiation from the electron when it's here, this side, and the electron is here, this side, is also shortened by a factor of 1 over gamma. Okay? So the apparent pulse of radiation is much, much shorter. We can think about it in an equivalent way by thinking, what is the observed frequency compared to the emitted frequency? Remember, the emitted frequency is just a cyclotron frequency, yeah? That's in the electron's frame of reference. We can write that down using our relativistic Doppler formula. Okay? That's the relativistic Doppler formula. For a large gamma, that's about 2 over 1 minus beta squared, and if you think about it for a bit, it looks like 2 gamma squared. Okay? It's the same kind of argument. So you can convince yourself both ways round that the radiation pulses, well, firstly the radiation is pulsed, and because it is pulsed, it must no longer be a single frequency. So that's the key difference. There will be a typical frequency of emission, therefore, Fs, which must be of order gamma squared times the cyclotron frequency. There's another gamma, so there's gamma to the fourth in the power, and a gamma squared in the typical frequency. So if I write that down, right, that is 1 over 2 pi gamma squared EB over M0. Okay? Now I will point out here, you have to be a bit careful in textbooks because obviously people, when they write down the cyclotron frequency, they can choose to write it down as either being the classical value, 1 over 2 pi EB over M0, or they can write it down as 1 over 2 pi EB over gamma M0. There's another gamma there, isn't there? So I'm only going to, when I write down the cyclotron frequency here, I'm going to write down the classical value, but you will sometimes see it written down the non-classical way, in which case there's another gamma factor there. Okay? Now, this argument is telling you that because the radiation is pulsed, and these pulses are very, very, very short in time, right? Well, let's calculate what that pulse duration is. The pulse duration is something like 1 over gamma squared Fc. Okay? And the pulse period, which is how long the electrons take to go around in a circle, is something like gamma over Fc, right? So this is the cyclotron frequency modified by that factor gamma. Yeah? I've just done 1 over that to work out how long the electrons take to go around in a circle. Okay? So therefore, the pulse length is equal to T over gamma. Now remember, gamma here is about 1,000 or so. Okay? Let's put some numbers in. So remember what I said, that we can build these devices, and they're called synchrotron radiation facilities. Look them up. There's a really big one in Oxford. The typical energy is order GeV. One in Oxford is 3. Right? And typical magnetic fields that we can manufacture cheaply are about 1 Tesla. Okay? So those are the kind of things we can physically do, practically. So in that situation, we have gamma is about 2,000, close enough for what we're doing. And the cyclotron frequency at 1 Tesla is 28 gigahertz. Okay? The revolution time, which is this relativistically modified cyclotron frequency, is 71 nanoseconds. It's been shortened by a factor of 2,000, yeah? This is 2,000 times less than that, okay, when I obviously invert it. The pulse length is 36 picoseconds. Okay? They're very, very different numbers. So what does that mean? That means that the pulse of light that comes out, okay, so I imagine a single light pulse with an amplitude of some amount at t equals 0. Okay? I take a Fourier transform of that, the frequency spectrum of the emission, okay, this is the Fourier amplitude, okay, that extends up to our typical frequency. That's our kind of cartoon picture of what the emission looks like. Okay, so that's the key statement. Synchrotron emission is broadband, cyclotron emission is single frequency. And it's because of the pulse nature of the light output. That's the key statement when it's getting stormy out. Now, that's for a single passage. Now, in reality, as a given electron, or let's say a bunch of electrons, goes by that tangential observer with a time spacing t, right? Then in reality, our frequency spectrum is really composed of many little thin lines, but that spacing between those different frequencies, okay, is of order fc over gamma, okay, which is much less than fs. Yeah, calculate those numbers. It's in the example sheet. Okay. So it is a smooth frequency spectrum. Now, in reality, when I do this Fourier transform, it doesn't look like that. It actually looks like this. It looks like that. Okay? What is this? The typical frequency is something like what we're going to show in a minute, which is what's called the critical frequency. They're related numbers, of course. So there's a critical frequency of emission where kind of half the power is emitted above it and half the power is emitted below. Okay? So this is not far different from that square. Yeah? It's approximately the same as our simple picture. Okay? So you get a variety of wavelengths emitted if you do this calculation more correctly. And you get a whole load of low energy photons. This is omega for the energy of each individual photon. This is how much power is, okay? And you get a smaller number of high energy photons. Each of the high energy photons carry more energy, isn't it? Okay? So the critical frequency is that halfway point. So let's calculate the relationship between that typical number and that critical frequency. Okay? So the first thing we can do, remember that the typical frequency of emission is gamma squared times the cyclotron, the classical cyclotron frequency. And we can simply write that down as gamma squared EB over 2 pi, and here's the mass of the electron, of course, because it's the only electrons we care about. But we already know that the bending radius rho of an electron in the magnetic field B is that, okay, because obviously the electron is heavier by a factor of gamma. So we can relate EB over ME to gamma C over rho. And the important thing here is we can rewrite the emission frequency in terms of gamma, the electron energy, and rho, the bending radius. That's a kind of universal equation. Okay. Now, when we do our fuller calculation, which we're not going to do here, it comes out to be 3 over 2 times that number. Okay. Gamma cubed C over rho. That is the critical frequency. Remember, the critical frequency is half the power is emitted at frequencies above that, and half the power is emitted at frequencies below that. The crucial thing that I'd like to remember is it's a factor of 3 over 2 between those two numbers. Okay? Now, if that's the critical frequency, the critical photon energy that goes with it is simply 3/2 h bar c gamma cubed over rho. So if I know what the radius of curvature of an electron is in a magnetic field, and I know its energy, I know what the typical photon energies are coming out are. And those are, let's write it down in kV, and again, sure you can calculate this to yourself, 2.218 E over rho, where E is in GeV, okay, that should be cubed, and rho is in meters. Okay. So you can see that we can describe the kind of emission of synchrotron radiation either in terms of the typical frequency, which comes directly from, it's just gamma squared times the cyclotron frequency. That's the thing to remember. Okay? If you can show that the critical frequency is 3/2 times the typical frequency, you should remember that fact. Okay? Obviously, because there's more photons emitted at low energy than there are at high energy, okay, there's many more down here, the average photon energy is lower than the critical energy. And so the other thing you should remember, that the average photon energy is not exactly 1/3 of the critical energy, but it's near enough. Okay? So let's write down those numbers. This is for diamond. This is our real light source down in Oxford. And here it's 3 GeV and 1.4 Tesla. And in the examples, I look at that source because it's obviously the one we have in the UK. Go through the examples and calculate all the numbers, please. Okay, very important. Critical energy 8.3 kV. The bending radius should come out at 7.1 meters. And the average photon energy is much lower. It's about 1/3 of that, about 2.8 kV. Why do we care? Why do we care that the energies are about a kV? Any idea? What can we do with those photons? What kind of wavelength does a kV photon have, roughly speaking? Well, the answer is it's about an angstrom or so, order of the atomic size. Calculate that number as well. So we use these photons because if we send them into a crystal of some sort, we'll get a diffraction pattern formed where the constructive interference happens at a certain angle which is related to the atomic spacing and related to the wavelength of these photons. Okay? So if we can measure the constructive interference angles, we can now know what the spacing of the atoms is. That's a procedure known as X-ray crystallography. So X-ray crystallography uses kV scale photons in order to work out crystal and subatomic, atomic scale structures. Okay? Like, for example, foot and mouth virus. Foot and mouth virus, the structure of that was worked out using crystallography by making a crystal out of many copies of the virus, which is a pretty amazing technique in itself. Okay. Now, all of that we've worked out so far, that is for one electron. What does it look like in reality? We have many electrons. And again, I'd like you to check using examples. Imagine I have a circumference L. Okay? And I have a number of electrons moving around. Obviously, when observed at a certain location, say the direction of observation, the apparent current is going to be equal to the amount of charge passing that point in any given time. Well, the amount of charge passing at any time is equal to IL over C, where L is the circumference and C is obviously the velocity of the electrons, because beta is equal to 1. So that means if I have 1 amp of current, okay, the number of electrons I have for 1 amp is something like 3.5 times 10 to the 12 electrons. Okay? Why is it interesting? Because the typical currents that we can store, the typical amount of charge we can store, related to obviously the same thing, is about an amp. It's actually about 300 milliamps is typical. Okay? Now, I'd like you to, these are all the same equations, right? The thing I haven't gone through here is, in a real storage ring, sometimes there are dipoles, and sometimes there are not. But I only get radiation coming out when the electrons are actually going through the magnetic field of the dipoles. There are spaces in between. That doesn't change anything about the total power emitted, because the total power is only coming from the dipoles. What it does change is it does change the circumference L. This L can be bigger than 2 pi rho. Okay, so when you work out a current for a certain circumference, bear that in mind. Okay, sometimes there is a magnetic field and sometimes there's not. Okay, now, if I know the power and I know the revolution time, TR, I can now work out the energy loss every revolution. We label that U0. And in the examples, I'd like to work out, it's very simple algebra, calculate the energy loss per turn, and for this particular case, I'm going to confirm for me that it's about 1 MeV, which is an interesting number. that tells you that a 1 GeV electron that moves in a circle in a 1 Tesla field, or thereabouts, will lose something like 10 to the minus 3 of its energy each orbit. That's a great scaling number. And that means it should last about 10 to the 3 orbits. Okay? And you've seen each orbit here is of the order of a microsecond or less, which means that an electron will last in a magnetic field of 1 Tesla for about a millisecond or thereabouts. Okay? If you know either the continuous power or the energy loss per turn, you should be able to then calculate, and again this is for diamond, the power radiated by each electron should come out to be about 86 nanowatts. You should try to calculate that, show you can do it. If you then put in an amp of current, say, the total power is equal to NE times the electron power, which is about 300 kilowatts. So even though one electron emits very little power, we need to feed the power back into that electron, need to feed the energy back into that electron in a time scale of the order of milliseconds. Okay? Which we won't go into. Actually, you have to feed it back in every turn or so. Okay? But because we have many electrons, we have 10 to the 12 electrons, the power emitted is enormous. Okay? There's one final thing. I know we're running slightly over, but hopefully you're enjoying this. I hope this is the most important lecture you go away with. This is how cool this is, isn't it? Let's calculate, finally, how many photons are emitted. And again, go through the examples. Well, clearly the number of photons emitted is simply equal to how much energy is lost per orbit divided by the average energy of the photons. Yeah? Okay. And we can stick in any one of those energies we like. Any one will do, because it's a scaling number, isn't it? We'll stick in the average energy, which is 1/3 of the critical energy. And this is the number of photons emitted per orbit. It's an interesting number. We can calculate that in a variety of ways, okay? But this way is simplest. And it's just proportional to gamma. And we blink a minute and we look at this here and we realise we can write that in terms of the fine structure constant. Okay? Which I think is a beautiful result. But we just rearrange it. Now remember, because this critical energy, sorry, this average energy here this is not an exact formula. This is an approximation. There's a slightly better formula. Okay? But the important thing is it goes proportional to alpha gamma times a constant number, which is really cool. Because now we can say gamma's, say, 1,000, alpha is about 1/100, so this part here is about 10. Okay? And this bit here is about 10 as well, so this is of the order of 100 for GeV, GeV electrons. So it emits on average 100 photons as it goes around in a circle, each electron. Okay? For diamond, show again, you can calculate it's about 360 photons per orbit. What does that mean? It means that the photon emission energy is a lot less than the energy loss per turn, which itself is a lot less than the electron energy. So despite the fact that the pulses are quite well defined and quite spread out in frequency, it's still a smooth energy loss for the electron. That's the important statement. Okay, so lots of ideas there. The notes will go through this. I have some questions on Monday, but we'll go straight on to Bremsstrahlung and Cherenkov on Monday. Okay? And I'm in the lab this afternoon and next Friday afternoon if you have any more questions as usual. Okay, thanks very much.